We already know that the closer an electron is to the nucleus, the harder it will be for it to be removed. So what is ionization energy? Simply defined, it is the lowest or minimum energy needed to remove an electron from the ground state or the initial energy level. The bigger the ionization energy, the more difficult it is to remove an electron. Kind of like a highly attracted couple will take more energy to separate. As a general rule, smaller atoms have higher ionization energies because the electrons are closer to the nucleus and are harder to remove. The effective nuclear charge is the attraction between the nucleus and the valence electron. The first ionization energy is the energy needed to remove the first electron. The second ionization energy is the amount of energy needed to remove the second electron, and so on and so forth. In the periodic table of elements, there are three basic patterns for ionization energy. Across each row, the ionization energy increases as the atomic number increases. The effective nuclear charge of an atom increases as we move across because the nucleus becomes stronger and thus holds the electrons more tightly. The second pattern is as you go down a column, the ionization energy generally decreases with the increasing atomic number. The effective nuclear charge of an atom stays the same as we move down a column in the periodic table, but the size of the atom increases and the electrons are farther away from the hold of the nucleus, so they are easier to take away and require less energy. So which element has a higher ionization energy, helium or neon? Helium, because its electrons are more tightly bound and are harder to remove, so they take a greater ionization energy to take them out. The third general guideline is that the transition metals, colored in gold, show a smaller range of ionization energies than the representative elements, which are the rest of the elements. Now, as with any guidelines in chemistry, there are irregularities or exceptions in ionization energy. Based on the guidelines, it should follow that boron has a higher ionization energy than beryllium. But as you can see, this is not the case. Beryllium in this instance has a slightly higher ionization energy. This difference, however, can be explained using the electron configuration of each element. Beryllium's electron configuration, He2s2, to boron, which is He2s2, 2p1. Boron has one more valence electron than beryllium, which is in the p subshell. The p subshell has slightly more energy than the s subshell, which means that it will be easier to take away electrons from. Another reason for boron's lower ionization energy is that beryllium's s subshell is completely filled and fairly stable, while boron's p subshell contains one electron, which will be easier to remove and will require less energy. Let's look at another example. According to our guidelines, oxygen should have a higher ionization energy than nitrogen, right? Yes, it should, but in reality, oxygen's ionization energy is less than that of nitrogen. The ionization energy of oxygen is less because in an oxygen ion, two electrons must share a sublevel. This increases the repulsion and makes it easier to separate them. In a nitrogen atom, the configuration is already fairly stable, so it takes a greater amount of energy to remove an electron. Oxygen would happily lose an electron to gain this stability, so it requires less energy. Let's recap. Smaller ions have higher ionization energies. There are three general guidelines to periodic trends of ionization energies. 1. Ionization energy increases across the periodic table as the atomic number increases. 2. The ionization energy decreases as we move down the periodic table and the atomic number increases. And 3. Transition metals have a smaller range of ionization energies when compared to the representative elements. There are exceptions to these patterns due to electron configuration of the elements.
Created using Powtoon.